This mini lecture will introduce you to the concepts of chirality, stereoisomerism, and optical activity. Well, let's start off with chirality. An object is achiral if it is superimposable on its own mirror image. So we've got a pen here. This pen happens to be symmetric. So we take the mirror image of the pen, and you'll notice that when we take that mirror image and we lay it on top of the pen, they match, everything's okay. That's what superimposable or superposable means. An object is chiral if it is not superposable on its mirror image. So here's an example. You've got this car, it's got this red wheel on this side and a green wheel on this side. You'll notice it's not a symmetric car. Take a mirror image of that car, and then when you try and line them up, you'll find the wheels don't match. That is not superposable on its mirror image. This car would be chiral. Now this applies to molecules as well. Now you'll notice that we have a molecule here that has two of the same thing attached to this carbon atom. So we've got two fluorines here. We take a mirror image of this molecule. Take a look at the mirror image. See how you got the green ones here in the front, and here they are here. And you got the blue one at the back, blue one at the back, red one front, red one at the front. So that's a mirror image of this compound. Now you'll notice in the next slide that what's going to happen is this is going to be able to be turned around and lined up so it exactly matches what we started with. They are exactly the same now. Now let's take a look at a molecule that has four different things attached to the carbon atom. We take the mirror image of that. Now if we attempt to line these two up, look what happens. The reds and the purple ones, the bromine and the iodine, won't match. They won't match up. This is all a consequence of the fact we have four different things attached to this carbon atom, and when we take the mirror image we find that we can't superimpose the mirror image on the original compound. That's what makes this molecule chiral. The two structures, the original structure and its mirror image, are called stereoisomers. Stereoisomers have the same molecular formula but a different spatial arrangement of atoms. And here is an example of that. These two things will be called constitutional isomers because you can see that this is an ether and these are alcohol, and this is an alcohol. But if you take a look at these two alcohols, there's mirror images of each other, and they have four different things attached to the carbon atom: a hydrogen, OH, F, and CH3. And those mirror images would be non-superimposable. So these are stereoisomers right here. Now in stereoisomerism we talk about these as being enantiomers, and enantiomers are non-superimposable mirror images. So these two compounds are considered to be enantiomers, because you can't take this and line it up with this one. They won't match up. Now we can actually distinguish between these based on a system similar to the EZ system, where we prioritize the atoms based on their atomic weight. So we can label this one fluorine 1, the oxygen would be 2, the carbon would be 3, and the hydrogen would be 4. And we can label both of those the same. And then what we do is we arrange this so the hydrogen is pointing away from us. Right, so what we did was move the hydrogen, sort of flip the molecule back and put the hydrogen backwards, and now we're just looking at the first, second and third priorities. And what we can do is we can designate arrows that show the order of those priorities, 1, 2, 3. Clockwise, that's designated R. Counterclockwise, that's designated S. So this molecule is considered an R molecule, this one's considered an S molecule. And we can name the enantiomers, and this one would be R, 1-fluoro, 1-ethanol. This would be S, 1-fluoro, 1-ethanol. We'll talk a lot more about this naming system in a little while. Now, one good question is, how do we even know that these things exist? How do we differentiate between enantiomers? How can we tell that they're any different? So if we take these two compounds, which are enantiomers, I want you to look at this carbon here and be convinced that it's got 4 different things attached to it. It's got an OH, an H, a CH3, and a CH2CH3. And this is the mirror image of it, and that would be this would be considered a chiral compound. And this one is actually S. This one is R, based on what we were doing earlier. It turns out they have the same melting point, same boiling point, same density, same pKa. So they don't look very different. How can we tell them apart? Well, the only way we can really tell them apart is to see how they interact with plane polarized light. So this is a typical light, and a typical light will have light that travels in all directions. You can see that here, infinite number of planes. But if we put a slit in there, we can block out everything but one plane of light, and this is plane polarized light that we're looking at here. Now if we take one of these, we'll take the R isomer and we stick it into a tank and we put it inside this light beam, it will actually rotate that light beam due to its chiral nature. Now this particular one, the R isomer, will rotate plane polarized light minus 13.5 degrees, so 13.5 degrees in this direction right here to the left. Now imagine what happens if we put the S in the same beam of light. Now it rotates it in the opposite direction, positive 13.5 degrees, or to the right. So it's going to rotate plane polarized light the exact same number of degrees, but in the opposite direction. Now the other one that went minus is called a minus or L compound, and a molecule that rotates light clockwise is labeled a plus or D compound. You might have heard of dextrorotatory and levorotatory. D is for dextro, it means to the right. Levorotatory, that was minus, and that was to the left. But there's no relationship really between plus and D and S. So it's not like every S molecule is a plus or a D. It could be either plus or minus. The whole RS thing is just due to an arbitrary naming system. This is actually due to the way that these interact with plane polarized light. And it bears repeating again, you can't determine by putting it in plane polarized light whether it's going to be R or S. The only thing you can do is to look at the actual structure and figure it out from there.